Good
Okay.
evening.
Yeah, good evening. In the last class, we left off with one particular problem. We'll start with the discussion of that problem. So it said fx is a polynomial with integer coefficients such that f of n evaluates to be a prime power, evaluates to a prime power for every integer n. Basically, a prime power is a number of the form p power k, where k is a positive integer and p is a prime. So f of n is becoming p power k for every integer n. Okay. And part A of the problem was saying if such a f of n, f of x exists, then there is a polynomial g of x such that for every non-negative integer n, g of n is a perfect power of a fixed prime number. Is a perfect power of a fixed prime number. So first of all, we have to figure out and we have to show that there is a g of x like that, which satisfies this condition. It is a perfect power of a fixed prime number if there is a f of x that satisfies this condition, the condition in the problem. So let's think about it. So f of x we can write as a polynomial like this: an x bar n plus an minus 1 x bar n minus 1 and so on till a1x plus a0. The question has said that f of x evaluates to a prime number for prime power for every integer n. So that means integer could be x is equal to 0 also. If integer is x is equal to 0, you get a0 is the value of f of 0. So a0 is a prime power p power k something, right? Similarly, you can say that f of 1 is also a prime power, f of 2 is also a prime power. The k's may be different, but it is p power something. Do you understand what I'm saying?
Yes, sir.
We have to assume that that is the property of my f of x. And now we have to think of, is it possible to create a g of x that is a perfect power of a prime number? So has anybody thought of any g of x which will fit?
Sir, does perfect power mean integral power?
Perfect power means it should not be a sum of powers. It should be one power.
Okay.
It should be p power something, perfect power, not sum of many powers, right?
Okay, sir.
So I will just tell you, you can define g of x as f of p of x. Think of what happens to this f of p of x. F of p of x would be what? F of p of x is equal to a n p power n x power n plus a n minus 1 x power n minus 1 p power n minus 1 till a1 px plus a naught, right? Correct? Do you understand what I'm saying right now?
Yes, sir.
Now, for every non-negative integer x, for example, let's think of g of 1, non-negative integer. You could also think of g of 0. Let's think of g of 0 first. G of 0 will be f of 0, and f of 0 is a0, and a0 is p power k, right? Correct?
Yes, sir.
Do you understand that g of 0 is a perfect prime power?
Yes, sir, because A naught is P bar K.
Hmm. Now think about it. Just hold on for a second. I'll be back in 2 minutes. Think about whether f of p of x is satisfying the conditions for other non-negative integers also or not. Okay. I'll be back in 2 minutes. Just think about it for a moment. Okay. So think about what happens if you do g of 1. G of 1 is f of p, right? And f of p would be an p power n and so on, right? That, right? Correct.
Yes, sir.
But we already know that f of x satisfies the condition that no matter every integer n, it evaluates to some p power k, right? So isn't this f of p simply an p power n plus that should be some p power k1, right?
Yes,
Are you understanding what I'm saying, everyone? Because that is the property of the f function itself. The f function itself always evaluates to a prime power for every integer n, right? Is everyone else understanding what I'm saying?
yes, sir.
We have chosen g of x as f of p of x. But f of x क्या होता है? F of x, whenever you give input to f of x, it evaluates to a prime power p per k, right? K could be different depending on the input. So if you give positive integer inputs here, you give g of 2, it is going to be f of 2p. And f of 2p is an integer, so it should evaluate to p power something, right? Then p power some constant.
Yes, sir.
So basically, we have constructed the required function. G of x is a function which satisfies the property given in part A as long as f of x satisfies the property given in the problem. Right?
So do we need to prove that f of px is unique?
No, we don't need to prove that it is unique. We need to prove that it is the power of a fixed prime number. What we need to show that is that fixed prime number will be p, obviously. It
Okay.
cannot be any other power, any other prime other than p, right?
Yes,
Because we saw that g of 0 was equal to p power k, which was a0, right?
yes,
So that is part A. You have to think of a g. Part B is asking us to prove that if you thought of the g in part A, then that g must be a constant polynomial. So we have to show that g of x is equal to f of p of x is a constant polynomial. Okay. So do you guys know any way to prove that a polynomial is a constant polynomial? Do you know any standard way to prove that?
so if its degree is more than the number of roots,
Degree is
sorry,
less than.
yes, yes, so the number of roots is greater than the degree.
Right. So if the number of roots of a polynomial are 5 and the degree was 3, then that means the polynomial is becoming equal to the same value 5 times. That means it must be an identity. anytime the number of roots is bigger than the degree of a polynomial, the polynomial is an identical identity. It's an always going to be equal to that value. I hope everyone knows this fact. If you have a quadratic function ax squared plus bx plus c, and anybody says that this is equal to 8 for x is equal to 1, 2, and 3, then basically that means that ax squared plus bx plus c is always 8 for all x. Everyone must be convinced of this, otherwise you cannot understand this. Is anybody having any doubt in this statement?
Sir, does that mean A and B are 0 and C is equal to 8?
No. That means that a and b can be anything, but the whole quadratic is always 8. I mean, what I'm saying is that this quadratic ax square plus bx plus c minus 8, this quadratic is always identically 0. So in fact, in reality, that will be true only if a is 0, b is 0, and c is 8. But in general, that doesn't have to happen. You could have a situation where they are non-zero and it always works out also. In this case, it
Sir,
is true what you're saying.
sir, I have one question actually pertaining to that.
Mhm.
We have considered initially that f of x actually about such generic polynomial thing. But
Mhm.
does it necessary to actually consider that g of x is also become the pertaining to f of p of x actually is what we have considered. Means it can't be a different polynomial as well, right?
But you have to, it can be, but then you have to figure out what it is, right? If you think of some other polynomial g of x, you have to make another polynomial which satisfies the properties of g, where g was supposed to be giving perfect powers of a prime number for any non-negative integer input. But it is difficult to think of such a polynomial if you think of it independently of f. If you think of a new polynomial which has no relation to f, and how would you make such a polynomial which is always going to give you prime powers? So that's why we are not thinking of anything other than, that's why we are involving f in it, because in the problem itself they said that f was following a property like that, right?
Yes. Okay.
We are thinking of it
Got it.
in terms of f because it is easier to figure out a polynomial like that. Otherwise, you could try and think of something, but it will be difficult. Like, I don't think there is a nice polynomial which you can say which will satisfy the property for g. So what we will show here for g of x is equal to f of p of x to be constant, we need to show that g of x has many roots or infinite number of roots, something like that. So if you think of g of x, let's write g of x as a polynomial bn x bar n plus bn minus 1 x bar n minus 1 and so on plus b1x plus b naught. Right now, I have not written it in terms of f right now. I am writing it in general. G of x can be represented like this. What we know is that g of 0 is equal to f of 0 is equal to p power k. We knew that from before also. From part A, we know that, right? Correct?
Yes.
Now, what I want to think about here is consider the input x is equal to m p power k plus 1. Think of the input x as m into p power k plus 1. If you put that input into your g function, you will get g of m p power k plus 1 is equal to bn m power n p power k plus 1 power n plus bn minus 1 m power n minus 1 and p power k plus 1 to the power n minus 1 and many terms like this. But notice that every time you are getting p power k plus 1 to the power something, right? Till b1 m p power k plus 1 and finally b0, right? Right? Here, when we took this m could be any integer or any non-negative integer m. Because g function satisfies its properties for what kind of integers? For non-negative integers, right? For any non-negative integer m, we are putting m into p power k plus 1 as the input to the g function, and we are getting this stuff, right? Do you understand what I'm saying?
Yes, sir.
Nothing I have done. I have just put an input and seen what the expression looks like. Now, what you can say by looking at this expression is that all the first terms here till here, all the terms are divisible by p power k plus 1, right? Correct? All of these terms are divisible by p power k plus 1, right?
Yes, sir. And complete terms are divisible by p power k also.
These terms are divisible by p power k. Obviously, they will be, this is divisible by only p power k, right?
Yes, sir.
This is not divisible by p power k plus 1, right?
Yes, sir. That's what I said.
So basically what this means is because it has to be, this has to be a perfect power of a prime number. Perfect power of prime p. We could not say that the perfect power can be k plus 1, right? It cannot be divisible by p power k plus 1. No?
No.
Because so many terms here are not, they are divisible by p power k plus 1, but this constant term is not, right? So the only way to say that g function is satisfying its criteria is if g function g of m p power k plus 1 is equal to p power k, right? G of m p power k plus 1 must be equal to p power k because this part you cannot write it as p power k plus 1. If you take modulo p power k plus 1 on both sides, modulo p power k plus 1, all of this will be 0 mod p power k plus 1. But we are getting this as p power k mod p power k plus 1. Right? So technically you can say that the g function mod p power k plus 1 is p power k, right? If you just look at it mod p power k plus 1, right?
Yes.
Correct, no? So what this means is that this result was true for all non-negative integers. For any non-negative integers, g of m p power k plus 1 is modulo is p power k mod p power k plus 1, right? So you can start putting any non-negative integer here, and that means that there are infinite roots for this, right?
Yes, sir.
For the g function, there are so many roots. For so many non-negative integers, it will satisfy this condition. So from there, we can conclude that since the polynomial g takes the value p power k infinitely many times, so it must be identically equal to p power k.
Yes.
And if g is identically equal to p power k, then by definition, g was equal to f of p power x. So f will also become a constant function. G function is coming identically equal to p power k because so many integer values, it will keep taking p power k value. and therefore f will also be a constant polynomial. We will look at another problem now. This question appeared in 2013. There is a polynomial f of x with real coefficients, and is said to be a sum of squares polynomial, sum of squares, or SOS polynomial, if we can write fx as equal to p1x square plus pkx square, where p1x, p2x, and pkx are all real polynomials. By real polynomials, we mean polynomials with real numbers as their coefficients. Now we have to select on the options. First one is if f of x is SOS, then coefficient of every odd power of x, odd power of x in f of x must be 0. This is the first option. B, if f of x is equal to x square plus px plus q has a non-real root, then f of x is SOS. Option C, if f of x is equal to x cube plus px square plus qx plus r has a non-real root, then f of x is SOS. And finally, last option is if f of x is greater than 0 for all real values of x, then f of x is SOS. So first of all, the definition of the term sum of squares polynomial is if it can be written as sum of squares of several polynomials where all of them are real polynomials. So we have to check all of these options one by one. Not very difficult question. The property is easy to understand. You have to just check the options and see whether you can figure it out or not.
Okay.
Sir, I think option A must be correct because if every odd part of x is not in the f of x becomes 0, then it will be perfect square of the sum.
No, you are looking at it in the reverse order. You have to say f of x is SOS and then figure out whether this is happening or not the reverse. F of x is the sum of squares type of situation. Then you have to say whether coefficient of odd powers is 0 or not, right? You are saying the second part first. Do you understand
Yes.
what I mean?
Yes.
There is a difference between P implies Q and Q implies P. They are not the same.
Sir, I don't think A is correct.
Why?
Sir, we can take some kind of example also.
Mm-hmm.
For example, P of P1 of x can be equal to x plus 1 and P2 of x can be x. Take every polynomial as x.
Hmm.
Then we do have the 2x term, which is like
Hmm.
has odd power but is not equal to 0.
And so all the other polynomials you can take as zero polynomials. And you can just take the first PA1x as x plus 1.
Yes, sir.
Then you will get f of x is basically P1x square. So that is x square plus 2x plus 1. It is
Yes, sir.
definitely SOS because it is following the pattern of P1x square plus 0 and all, right?
Yes, sir. But it has
But
uh,
the odd degree term here has even it is non-zero.
right.
Costa, are you understanding what is being said?
Yes.
So
Understand that.
that is a counter example. This is an
Mm,
example by which it is SOS, but it is not satisfying this,
mm,
right?
yes.
So this option is wrong. Now we have to think of other options.
I think even option B is also false because for fx to be SOS, the quadratic must be a perfect square. I mean, it should have repeated roots.
No, again, you're making a mistake of P implies Q stuff.
Okay.
Why are you assuming f of x is SOS?
Yes.
You have to look at this and say that what happens if it has non-real root and then think about it.
Okay.
F of x is right now given as x squared plus px plus q. Does everyone know what is completing the squares? Can you write it like this?
Yes, sir.
I hope everyone is aware that you can complete the squares like this here.
Yes.
Now, what is the meaning if it has a non-real root? Discriminant is less than 0, right?
Yes.
Discriminant of this is p square minus 4q is less than 0, which means 4q minus p square is positive, right?
Yes, sir.
If 4q minus p square is positive, then obviously we can write this as a square of some real number. Do you understand what I'm saying? If 4q minus p square is positive, then we can write it as some root of 4q minus p square by 2 whole square, right? And then f of x has been written as one polynomial square plus another constant polynomial square. Do you understand why option B is correct?
Yes, sir.
Option B is correct because quadratic polynomial like this can be represented by this. And if it has non-real roots, the discriminant is negative, but means this part is positive. And if this part is positive, you can write it as square root of that thing whole square, which becomes our constant polynomial P2x,
Yes, sir.
right? So the whole f of x has been written as P1x square plus P2x square, which means it is SOS then. Option C, if you think about option C,
Sir, it must have a real root at least one. So for some part, it will be negative also.
option C, they are saying it has a non-real root. Function has a non-real root. So if it has a non-real root, then it has two non-real roots, right?
And the other one has to be a
And
real
there
root.
is a real root. And if one real root, then function is either increasing or fully decreasing, right?
Yes, sir.
If there is one real root in a cubic polynomial, it is off the graph will be like this or like this, going up or going down forever, right?
Yes, sir.
Which means that it will be below x-axis for some portion, right? If the function takes negative values for some portion, then it cannot be written as sum of squares.
Right.
Is everyone understanding what I'm saying, right? If the value of this polynomial is becoming negative for some real numbers, then can it be written as sum of squares?
No.
No. You cannot write it as sum of polynomial squares if the polynomials are all real polynomials. Therefore, you can say that this cannot be SOS. Another way to think about it is look at f of x like this. As x tends to infinity, f of x tends to minus infinity here. Which means it is so negative. For large negative values, the function is very negative. And if it is very negative, that means it will take negative values. And if it takes negative values, that means it cannot be written as sum of squares. I hope everyone is understanding.
Yes, sir.
So option C is false. And then we have to look at option D. If f of x is always greater than 0 for all real values of x, then f of x is SOS. Right. So
So we have an example, x square plus x plus 1.
example will not be enough here because an example is not a counter example, right?
Yes, sir.
You understand the difference between a counter example and an example?
So what I said that if we take x square plus x plus 1, like assuming fx to be x square plus x plus 1,
Mhm.
so it follows the first condition that it is positive for all real values of x. Even then it is not SOS.
No, even then it is not SOS.
Yes, sir. It is positive, but it's not SOS.
Why is it not SOS? You have not understood only. That is
No,
SOS by
actually,
part B.
actually, in the first part itself,
Yeah,
actually, you
part
have
B it is
shown us, no? X
SOS.
plus,
Yes, sir. Yes.
yes, part B, yes, part B. So,
It is over. What you have given an example is definitely SOS by part B.
Yes.
What we have to say here is if f of x is greater than 0, is it SOS? For all real values of x, is it SOS? And it doesn't have to, you cannot prove this question by giving examples. You have to prove it properly. Do you understand what I'm saying?
Yes, sir.
If you want to disprove something, you can do it by an example. You cannot prove something with examples. Right?
Yes.
What you will say here is f of x is greater than 0 for all real values of x, which means all roots of f of x are non-real, right? Correct? No?
Yes.
And if all roots are non-real and f was a polynomial with real coefficients, then roots are in pairs. Roots are always in conjugate pairs then, right? And if roots are in pairs, then f of x is the product of quadratic polynomials. Why? Because roots will be like this: x minus a plus ib, one factor, and another factor would be x minus a minus ib, right? So if you multiply these two, you will get x minus a whole square minus ib plus ib. So minus I square b square. So plus b square, right? This is a factor, no? For each pair of complex roots, which are conjugates of each other, we get a quadratic factor, right? Correct?
Yes.
Shrish, are you understanding what I'm saying?
Yes, sir.
If you get quadratic factors like that, each of these factors is SOS. Because it's the sum of squares. It is obviously sum of squares, right? Now, if you multiply out a product of SOS type of factors, you will end up with an SOS polynomial.
Right.
You can check it yourself. If you have x minus c whole square plus d square, don't worry about other factors for now. Whenever you do this multiplication and expand it, it will always be SOS. Right?
Yes, sir.
I hope everyone is understanding how D is coming correct. Okay, we'll move on then to the next problem. Suppose f of x is a function from R to R, such that f of x is equal to f of x to the power 2013. First part is show that there are infinitely many such functions. Infinitely many such functions. And second part is show that exactly four of these functions are polynomials. So you have to think about how you would solve an equation like this, or how you would figure out the possible functions here.
Yes.
The first thing whenever you have a functional equation is to choose some nice values and see some patterns if you can figure out some pattern.
Yes, sir.
Right? So let's choose values like 0 first. Let's put x is equal to 0 in that equation. X is equal to 0, you get f of 0 is equal to f of 0 to the power 2013. Right?
Yes, sir.
Correct. So definitely this says that f of 0 is equal to 0 fits this, by the way. Right? So right now, one possible value for f of 0 is 0. It could be others. We don't know for sure right now. But f of 0 is equal to 0 definitely fits this equation. Right?
Yes, sir.
If you put x is equal to 1, you'll get f of 1 is equal to, again, similar thing, f of 1 to the power 2013. Right? So one possible option is a constant, right?
Yes, sir.
Do you understand what I'm saying? You can say that f of 1 is also 1. That will also fit, right? Correct?
Yes, sir.
F of, so basically we are having f of 0 could be 0. By the way, f of 0 could be 1 also fits, right?
Yes, sir.
Uh, and minus 1 also fits. If you put minus 1 also, you will get f of minus 1, and this is minus 1 power 2013, which works out.
Yes, sir.
So far I have figured out 3 options for f of 0. Similarly, from here, we could say f of 1 could be, again, it's literally the same condition. So there are 3 options for f of 1 also, right? It could be 0, 1, or minus 1.
Yes, sir.
Do you understand what I'm saying right now? Right? What about f of minus 1? F of minus 1 is f of minus 1 power 2013. And if f of minus 1 is 1, it won't work, I think. No, it will depend on the value of f of 1, right? Basically, what I'm saying is if f of minus 1 is minus 1, then this part works out nicely. Uh, right. Okay, we have to focus on how we'll prove infinite number of functions. F of minus 1 could be minus 1.
So can we go this way? Like we can substitute f of x to be t. So we get f of t equal to t power 2013, right?
Hmm.
And since f goes from R to R and t also goes from R to R. So so we must have at least uh, uh, let me reframe this.
Hmm. Uh,
So we must have at least one. Wait, sir, I'm a little bit confused, but
see, we have functions from R to R. We have to figure out 0, 1, and minus 1. What is happening? Let's think about this result. Can we put f of 0 as 1? And can we put any arbitrary order here? Let's think of that. Is it possible? Something like this. F of 0 is 1, then 1, 1. This side is 1, f of 1. Then if f of 0 is 1, f of 1 must be 1, right?
yes, sir.
Do you see what is happening? This is not possible, no? If f of 0 is 1, you have to have f of 1 also 1, right?
Right.
And if f of 0 and f of 1 are 1, f of minus 1, minus 1. Can it be anything? If f of minus 1 is minus 1, you get f of minus 1 is minus 1, minus 1. That fits though. So what we have is f of -1, we are not getting any condition from here. But what I can see from this is at least that constant functions could be a solution, right?
Yes, sir.
Constant functions, for example, constant function f of x is 0, f of x is 1, f of x is -1. These three constant functions are definitely solutions, right?
Yes, sir.
Dekho, every time it will be -1 fits, 1 fits, 0 also fits, right? So these are three constant functions and these are polynomials, by the way, right? You can call them as polynomials which fit, right?
Yes, sir.
Now, how can there be infinite functions? That is what we have to figure out. How is it possible to have infinite functions like this, which satisfy this property, right? So for infinite functions, let's say we decide f of 0 is 0, f of 1 is 1, and f of -1 is -1. If we fix these three, can we determine what will happen to f of 2 and all? F of 2. There is no restriction on the other values, right? F of 2 is f of 2 power 2013. F of 2. For other values of x, what can we say? Basically, I feel like for any other value of x, you have to still take 0, 1 and -1 only. Because you are trying to solve an equation where
So can we define it this way that means we have already defined that f of 0 is equal to 0, f of 1 is equal to 1, and f of -1 is equal to -1. And this is actually going from R to R. So by that way, we can found that every elements of say for that first set is A. So for the first set of A, we will get the distinct value of the second set is that is B. So by that way, we can say that we have an infinitely mean such mapping of
I,
functions.
how are you saying infinite though? Infinite, how is it?
Because this real number set itself contain the infinite up to infinite elements. Right? So likewise, we can say that it will contain the infinite distinct elements for the next set during the mapping. So
But the
likewise, we
problem
can.
is that they have to satisfy this condition. So far, we have gotten this condition because we chose these values, right? If how do we know whether f of 2 satisfies it or not, right? Just because there are infinite elements, not all the functions will satisfy this, no. Do you understand what I'm saying?
Yes.
The total number of possible functions is obviously infinite, but we have to make sure that it also satisfies the condition, right? So, basically what I am feeling is that if the only way this condition works is if it was 1, -1 or 0. If f of 2 is 0, it works, right? See,
Yes.
if
Yes.
f of 2 is 1, again it will work. If f of 2 is 1, you get f of 1 and f of 1 is 1. And this side is also 1 part this, right?
No,
And
but
f of
sir,
hmm.
In this case, f of 2, can it holds multiple values? Because in that case, that won't be a functions, right? Suppose means okay,
We are taking possible choices, not they will not
okay,
simultaneously. It will not be all three. We are saying
okay,
what are
I
the
got it.
choices for f of 2, right?
Yes, I got it, sir.
If it is -1, it also satisfies. If f of 2 was -1, you would have gotten f of -1 is -1 per 2013, but we have already put f of -1 as -1. So this will also work out. So basically what I'm saying is if these are fixed, after that it didn't matter what f of 2 we chose, as long as we chose one of the three, right? Do you understand what I'm saying?
Yes.
If you fix the 0, 1 and -1, let's fix them as like this. 0 goes to 0, 1 goes to 1, -1 goes to -1. After that, as long as any arbitrary number a is mapped to these three, it will always satisfy the condition, right?
Yes.
Because 2 was a random number that I had picked. We could have checked it for any other number also. So what I'm saying is for every other real number, there are three choices. You can always put 0, 1 or -1 as long as your basic three numbers here are set, right? Do you understand what I'm saying? So the number of functions that will satisfy the condition, there are infinite such functions because these three are fixed and then there are 3 power infinite number of possible functions, right? Is everyone understanding why there will be infinite functions like this which satisfy this? The
Not
reason for,
exactly.
huh? Bolo?
So not exactly I'm able to understand.
It is very simple. We are setting the three inputs 0, 1, -1. We are setting them equal to 0, 1, -1, right? Any other element, how to choose what should be the outputs? I'm going to say for any a belonging to real -0, 1, -1. F of a can be either 0 or 1 or -1. And if you do this, then it will automatically satisfy this condition. Check this claim. My claim is that for any number f of 10, if you can choose either 0, 1 or -1 as the output of f of 10, it will satisfy this condition.
Yes.
Do you understand what I'm saying?
Yes, sir.
F of 14, as long as your first three are fixed and your outputs are always going to this set, no other things are allowed. All the real numbers will be mapped to 0, 1 or -1. You can pick whichever one.
Yes.
So how will you count the number of functions in this set? Number of such functions which satisfy is obviously going to be 3 power infinite elements in this domain, right?
Yes, sir. Because every element has three choices.
All the elements other than these three have three choices, right? And as long as you build your functions in this method, you will always satisfy this condition, right?
Yes.
So there are infinite functions, obviously. We have already found three of those functions. Three of those functions are polynomials, which are constant polynomials. Three of those functions are what? The functions f of x is 0, f of x is 1, and f of x is minus 1. Right?
Yes.
Yes, sir.
These three functions are constant polynomials that are part of these infinite functions. Correct?
Yes, sir.
We have to find the last one, the fourth one, which they are saying. There are exactly 4 such polynomials. So let's think about it. We have f of x is equal to f of x power 2013. So if we think about the degree of the polynomial, hmm,
So f of x equal to x power 2013.
x is equal to x power 2013, and you'll have f of 201 x power 2013 is equal to this side would be x power 201. Okay, yeah, it is working out, right?
Yes.
Right. F of x is equal to x power 2013 is definitely going to satisfy for any x, right?
Yes, sir.
Right. Yeah, so that is the fourth one, I think. That is the fourth polynomial. That polynomial, by definition, will satisfy, right?
Yes,
Yes.
sir.
So we have 3 constant polynomials, and fourth polynomial is f of x is equal to x power 2013. Fine. That is correct. Okay. So interesting question where we had to think about the possible conditions on 0, 1, and -1. Without that, we cannot figure out what to do.
Yes, sir.
A few questions that you should try for tomorrow. First one is this. A polynomial p of x of degree 7 satisfies p of n is equal to 2 power n for n is equal to 0 to 7. Find p of 10. Question 2 is, consider a sequence of polynomials with real coefficients defined as p0x is equal to x square plus 1, x square plus 2 multiplied x square plus 1009, and p of k plus 1x is equal to p of k x plus 1 minus p of k x for k is greater than equal to 0. You have to find the least number n for which p of n of 1 is equal to p of n of 2 is equal to p of n of 5000. Try these two problems. We'll continue the discussion tomorrow, these two questions. And we have 2, 3 more problems that I wanted to show.
Okay.
After that, we will start the next topic. So polynomials, more or less, we have covered all types. So some more problems I wanted to show. These two you need to try and we'll discuss tomorrow.
Okay.
Have you written down the questions? Just write down the question.
Yes.
Okay. We'll continue tomorrow then. That's all for now.